Alright, so this is going to be a video walking you through page 2, and I want to remind you guys that you should have already filled out page 1 and have this list of perfect squares. And down below, when we take the square root of each of these numbers, so if I take the square root of 81, for example, that answer is considered rational because the square root of 81 is 9 and 9 is an integer. So if it's a perfect square and you take the square root of it, it's rational. But what about when you take the square root of a non-perfect square? That's irrational. And so now we're going to learn how to simplify the stuff that is non-perfect. Now, before we do this, I want to remind you guys that when reducing fractions, you pretty much have two options. You have the long way and the short way. And that's going to be kind of how we split it up too with the radicals. First method A, and then we're going to talk about method B. Now, first I'm going to focus just on method A with reducing a fraction. You can take both of these and divide by 2. And then you can realize that 12 and 15 have another common factor of 3, and then you have to reduce again to get the 4/5. So you can kind of break it down, but eventually you'd get 4/5. Over here, if you identify the greatest common factor, you can reduce just kind of in one big fat step. And again, the greatest common factor of 24 and 30 is 6. And so you could reduce by identifying here what we call the greatest common factor, or the GCF. Now, our factors this time are going to be considered perfect squares. So I will come over here to the GCF method eventually, but I'm going to wait on that because this is considered to be the shortcut. And the shortcut won't work all of the time, and also the shortcut won't work with variables. So I'm going to hold off on method B for right now. And first we're going to start over here with method A. Okay, so we're focusing on method A, the factor tree. And for a factor tree, your goal is to take the prime numbers that we talked about, the prime numbers under 10, and you're looking at the numbers 2, 3, 5, and 7, and you want to try to create a factor tree using just these values. So the first prime number that goes into 80 is 2, and it's 2 times 40, and you just kind of draw like a little V, so 2 times 40. Then 40 is 2 times 20, 20 is 2 times 10, and 10 is 2 times 5. So now what we have here is a 2 times 2 times 2 times 2 times 5, and that's how we get 80. So the idea here is that we want to pull out any perfect squares that we can when we reduce. Anything that is a perfect square, we want to take it out. Now the 2 times 2 right here, you guys know that that's 4, and we do know the square root of 4 is 2. So that's this 2 that I've taken out right here. Now this 2 times 4 right here, sorry, 2 times 2 is a 4. And we know the square root of this 4 is also 2, and that's 2 right here. So the only thing we don't know the square root of right here in blue is going to be when I try to take the square root of 5, and that is all that's left. So out here, 2 times 2 is 4, and 4 times the square root of 5 is simplified. Now to check to see if we're right, we're going to take out our calculators here, and first I'm going to have you guys just take the square root of 80, and the square root of 80 is 8.94 blah 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 blah. Alright, so to check to see if we're right here, I'm just going to take the square root of 5 and multiply it by 4, and it should be this same decimal. So first I'm going to take the square root of 5. Now if I just multiply by 4, boom, there's the 8.944 blah 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 blah. So it's the same thing. Alright? Now I think the easiest thing for me to do is to go ahead, and once I've shown you one example, I'm going to go ahead now and show you another example down here with the 294. If you make your prime factor tree, it's 2 times 194. 3 goes into 147, and it's 3 times 49. And then we have 7 times 7 is the 49. So when you're looking for your pairs here, 7 times 7 is 49. And since we know the square root of 49 is 7, we're going to take out a 7. And then all we have left underneath the radical is going to be this 2 times 3, which is 6. So that's essentially what we're doing here, y'all, okay? We're just going to take these numbers and break them down into a prime factor tree. And since we're looking for perfect squares, we're going to circle anything times itself because the square root of 49 here would be a 7. And so our goal is to take out anything that is a perfect square. Now I'm going to come back up here, and I'm going to show you here the greatest common factor method. The GCF method says that if you can identify from this list of perfect squares one of these numbers that goes into it, you can start there. So what we're saying here is that 80, if you recognize that 16 goes into 80, you can immediately break 80 down into a 16 times 5. And since we know the square root of 16 is 4, immediately we can take that out, and all that we are going to have left here is the 5. okay? So I'm going to show you guys real quick that method B also works with 294. 294, here, I'm going to show it right here, is actually the product of 49 times 6. So if you take 49 and take the square root of it, that's going to be 7, and the 6 is all that's left. All right, so we get the same answer using our shortcut as we did with the prime factor tree, and we circled away our 7, and 2 times 3 was left. Now, a couple of other things I want to point out in the video is that your method, either method will work if something's already a perfect square. So for example, you guys already know that the square root of 100 is 10. You already know that 100 is a perfect square. But let's say in the middle of doing a bunch of these problems, you don't recognize that a number is a perfect square. For example, I'm not convinced that if you saw the square root of 441, I'm not convinced that you'd know it was a perfect square to immediately tell me the answer is 21. So I wanted to show you guys that the method A will work and help you realize when something is a perfect square, and here's how that goes. So if you do the prime factor tree for 100, it's 2 times 50, which is 2 times 25, which is 5 times 5. All right? So now when you circle away your pair, you've circled a 2, so 2's out. You've also circled a 5, so 5's out. And there's nothing left. So you've just got the 2 times the 5, which is 10, and then you're like, oh yeah, okay, I knew that 100 was the perfect square, and its square root here is 10. Now, another thing. Fractions, when you reduce them, they can already be simplified. So for example, if I wanted you to reduce 3/7, you'd tell me it was already reduced. If you wanted me to reduce 13/15, again, you'd tell me it's already reduced. So back to this problem, let's say we're taking the square root of 42. So you know 42 is not a perfect square, and so you're going to start your prime factor tree. So you've got your 2 times 21, and then you've got that's a 3 times 7. So here we have 2 times 3 times 7 is 42, and none of those repeat, so we don't have any pairs to circle out. So here in this case, you would literally just say that it is already simplified. You'll just write down it is already simplified. Alright, so I've already shown you guys this example, and what I've got here on screen too is the prime factor trees. I'm going to actually ask you to stop the video, and I'm not going to work through any more examples on page 2. I'm going to have you guys actually just try those examples, and then you're going to move on over to page 3 and try page 3, and then you're just going to check an answer key for pages 2 and 3 to make sure you're good to go. And that concludes the video for page 2. Thank you.